last talk of this long session of lectures, Mario Sanchez.
Right. Thank you so much. And thank you all for staying. I saw that I'm like the 32nd speaker or something truly very tiring. So luckily we have a lightweight topic. We're studying derived categories. But my goal is to try to give you an overall picture of what's going on. So at the core, I'm an algebraic combinatorialist. I care about how combinatorics appears in homological algebra, algebraic geometry, representation theory, and so on. And as such, it's my obligation that to have a favorite geometry, which is toric geometry. So if you haven't heard about this, this gives you some nice bridge between convex geometry and algebraic geometry. Given a nice polyhedral fan sitting inside a lattice in a nice way, one gets a variety with a very big torus action on it, the toric variety. Now, I don't want to talk about polyhedral fans because I want to kind of stay near objects everyone has seen. And so I'm going to be talking specifically from lattice polytopes. So this is like a generalization of a polygon with vertices in the lattice. And this gives rise to projected toric varieties with specific embeddings. So here, for instance, we have this trapezoid, and this will give rise to a toric variety, the Husserl surface H1. The point of toric geometry is that it allows us to transfer concepts and ideas and techniques from one side to the other, and has been very fruitful amongst both combinatorialists and algebraic geometers. So let me spell out one such correspondence. So I'm going to begin talking about deformations of a polytope. So this symbol here will be the deformation cone of P, will consist of lattice polytopes, which are deformations of P. This is some statement about normal fans, but instead I'll give it kind of intuitively. What we're going to do is we're going to take P and we're going to take the vertices, and we're allowed to move all the vertices, but all edge directions must remain the same. So you cannot change the edge directions, but you can move around the vertices. Vertices can even collide. And so let me show you an example. So on this Husserl surface, we have the following deformations of this polytope. Right, we have the natural ones, which are just making the polytope bigger. But we can also, for instance, take these two vertices and move them in, maintaining the edge directions and have them collide with the previous vertices to create a triangle. We can also get the edge and just a single point by just shrinking. Note that we can't get the vertical lines.
So you lost edge directions, right? That's
right. Maintaining edge directions until you collide. Yeah. Once you collide, there's no.
You can get new directions, but you can remove directions.
That's right. Exactly.
Why can't you get a vertical one?
Yeah.
Well, these two vertices here are kind of hard to make vertical. I challenge you to try.
Fix a triangle and just.
Yeah, so you can move this until you hit here, and then what? Well, you can't change, and in fact, yeah, let's talk about the triangle. So for CP2, we have this triangle, and this polytope is actually very rigid in the sense that we can't degenerate it. And in fact, the only deformations you have are the dilations. So here I'm telling you sort of Neff cones of varieties. And the statement is exactly, under this bridge, these deformations are describing the line bundles on the polytope. So if you take these deformations up to lattice translations, they're describing a special class of line bundles. Now, if you're not an algebraic geometer, you probably still have heard the word line bundle. The point being that a lot of the classical questions that we care about, we know how to phrase in terms of line bundles and vector bundles and more generally sheaves. So they're in some sense the key object to study. And what I'm telling you is that for a special class of them, you're studying polytopes. Okay? So part of what I'm interested in is filling out this dictionary, trying to understand what various different invariants of algebraic geometry look like in convex geometry. The invariant I want to talk about today is the derived category of a variety. So again, it's probably a word you've heard, and I'm not going to be able to define it, but the basic premise is that we have an abelian category. We can associate a derived category that in some sense is supposed to be encoding the cohomological properties of the original category. Think of some universal cohomological invariant. So to a nice variety, I'm going to associate a derived category of the so-called coherent sheaves. The objects of this category are complexes of sheaves, which include line bundles, which I just told you are kind of like polytopes. So you have some sort of polytopal elements in here. And the morphisms of these categories are very, very hard to compute. It's a difficult invariant. Now, why should you care about such an invariant? Well, if you don't believe proof by intimidation, then let me try to give you a kind of different reason. The main idea is that once you pass this derived category, you start to pick up some very interesting equivalences between different objects. So one such equivalence, for instance, comes from the representation theory of quivers. So here, I'm assigning vector spaces to my vertices and linear maps to my arrows. and call these representations of quivers. These two quivers, when you look at them just from the representation point of view, are different. However, once you pass to the derived category, they are the same. And in particular, this tells you things like the number of indecomposables and so on. You also get such equivalences between varieties. However, the most interesting type of equivalences you get are those that happen between different fields. I'm sure you can ask around and have someone tell you about homological mirror symmetry, which is one such example. But instead, I want to focus on a result of balancing. He found, and this is kind of what started the serious study of derived categories as their own objects, he found that the derived category of CP1 can be described as a certain category of modules over a quiver, namely the chronicle. And so here you have some very strange thing. So you have sheaves on some space and you have representations on some quiver. And this gives, in many ways, a very explicit and concrete calculation of that original category. Okay. Now, this phenomenon actually happens for other varieties as well. This is something that Baer and Blundell were doing. They found conditions for when you get such quivers. And the conditions go something like this. If you have some collection of, I'm going to say in a special case, if you have some collection of nice line bundles on a nice variety, that satisfy two technical conditions. One, they're full, and two, they're strongly exceptional. Then you get such an equivalence between a quiver and your variety. And in fact, the quiver is fairly easy to compute. Just a note, the quiver might have relations, but that doesn't change too much how explicit it is. Full here is some statement about how it generates the category in some classical sense. And strongly exceptional is some statement about the vanishing of higher extensions between these line bundles. We call such things full strongly exceptional collections. Now, finding such things is difficult. It was conjectured for a while that every smooth projective toric variety had such a collection, but that was proven to be false. And so it's kind of unclear sort of how to find these or how common they are. Well, you see the word line bundle, and I told you those are polytopes. So you should immediately have the question, well, can I just view everything as some sort of polytopic construction and leave algebraic geometry behind and do calculations on explicit polytopes? And that's exactly what the work I want to talk about is. It gives a convex geometric method of building these full strongly exceptional collections of line bundles. Now, I'm not going to talk about the translation process because it's complicated. The main tool I use is this thing called the covariant constructible correspondence, first kind of noted by Blundell and then proven in a DG covariant sense by FLTC. Just briefly for the experts, what this is doing is it's giving you an embedding of the DG category of perfect complexes into nice complexes of Rn. These are compactly supported and constructible on Rn. They actually even tell you exactly what the image is. And the key point about this is that the ample line bundles, viewed as a complex in degree 0, they map to kind of skyscraper sheaves on that polytope. Take the constant sheaf on the interior of that polytope, push it forward in a DG sense. And so these objects over here are much easier to work with than these. For instance, if you subdivide a polytope, you might be able to immediately see how that gives you an exact sequence over here. But luckily, we don't have to think about this sort of algebraic geometry right now. We can view everything combinatorially. And so now this is what I want to do. So I need to tell you what it means to be strongly exceptional and what it means to be full on the combinatorial side. So a collection of polytopes are going to be strongly exceptional if the following strange condition holds. If you take one polytope, take the set difference from a lattice translation of another one, that should be contractible or empty. Again, the set difference of polytopes. Not something you've studied before. I haven't. I've definitely never seen it. So let me give you an example. So for CP2, we have the following three polytopes. I'm going to call this O, O1, and O2 for mysterious reasons. Then you can immediately see that the set difference of any lattice translation is contracted. Lattice translation. So once I translate this triangle, I can move it here, or there, or somewhere on the boundary. But no matter how I do it, it's contracted.
Contractible here in the sense of topology?
In the sense of topology, yeah. Okay, so this is a strongly exceptional collection of polytopes. Note, we cannot add this third dilation of the triangle because you can move this lattice point in the middle. That's a lattice translation, take it out, you have a punctured disk, not a triangle. So this is strong exceptionality. Fullness, now, I don't really have time to actually talk about the full definition of fullness. Something about CW posets being inside the class of deformations of polytopes. So instead, I'll give a special case, which will be sufficient for these small examples I'll show you. So here's a special case. A weak subdivision of a polytope is a collection of polytopes. Everything's in my deformation cone. the union of the polytopes better be equal to Q, weakly subdividing. And now I'm gonna have the condition that my polytopes are allowed to overlap, but the overlap better be a deformation of my original polytope again. Okay. So this is, maybe I shouldn't even use the word subdivision, right? Usually you want the intersections to be faces or something. So for instance, for CP2, we have this polytope. We can subdivide it in the following way. I can take the second dilation of my simplex, put it there, take another second dilation, translate it off. Note that the intersection is a single triangle, and then take the third one up there. The intersections here are all smaller triangles or vertices, points, if you take the three-way intersection. And here I'm describing some exact sequence on O3 in terms of O2, O1, and O. Okay, I will say that a collection is full if every polytope in the deformation cone can be weakly subdivided by translations of polytopes in P. So if your collection is sufficient to weakly subdivide everything, including translations, I'm going to call that full. Again, this is a much weaker sense than the full sense one needs for stronger results. So for instance, for this, it's full. As kind of the argument I gave in the previous slide kind of extends to any translation. And I'm going to call these full strongly exceptional collections of polytopes if they satisfy both conditions. Of course, the theorem that I feel kind of still insane because I haven't told you the full definition is that this condition is exactly the correct condition and that it implies full strong exceptionality. So it suffices to study this polytopal condition. Okay. So let's do an example. We're going to do proof by picture of a calculation. I claim for the trapezoid, first surface by surface, these four give a full strongly exceptional collection. For exceptionality, you just look at it. Take the triangle. There's nowhere to put it where you will create something bad. It's always contracted. For fullness, I'll just show you a general argument and a generic element in this deformation. And in fact, actually, you should be able to do this. If I give you a few minutes, you'll be able to figure out how to subdivide it using kind of the idea I used in the previous slides. First, I'm going to subdivide things strip by strip. In the bottom strip, what I'm going to do is I'm going to take my trapezoid and then translate it across. So here's the first one. The next one will be translated over. Note the intersection is one of the triangles. I'm going to go all the way across and do this strip by strip. So I kind of want you to appreciate this. This is a proof by picture, a polygon proof by picture that calculates the derived category of H1. Right. Now, of course, as soon as you leave dimension 2, how do you show that set difference of polytopes are contractible? How do you study subdivisions? These are difficult problems. So it's not like we've trivialized everything. However, for certain varieties, we know a lot about them. So let me tell you the objectively best variety. This is the Permutahedral variety. This is a toric variety for this polytope. This polytope here is a convex hull of a generic point under the orbit of Sn, right? Or equivalently is the fan of the type A Coxeter arrangement. You might know this for the geometers. This is the Loss-Manning compactification of M0n, like chains of projective lines with marked points and so on. For algebraic combinatorialists, the reason we care about this so much is that if you study the deformations of this thing here, you'll find polytopal models for almost anything you care about, like matroids and graphs and pressure complexes and so on. You can go look at Federico's massive paper to have lots of examples of this. And if none of these things convince you, I can appeal to authority. This variety is one of the central variety in Junihau's thesis. And in some sense, the intersection theory of this variety is really kind of what underpins a lot of the Hodge theory of matrix. It's a very beautiful variety. And so I know a lot about generalized Permutahedra, so I figured I should study this, and it works. Theorem, we have the following full strongly exceptional collection of polytopes for the Permutahedral variety. And no, you cannot escape matroids. The polytopes you need are exactly these loopless Schubert matroids. And if you don't know what that means, come talk to me. We can talk about matroid theory. Now, for the experts, if you're familiar with the literature on the study of the Permutahedral variety, there's a good reason to suspect that this is the correct class of polytopes to study. But first, let me talk about a few other generalizations. There's a stellahedral variety, which is a kind of augmentation of the Permutahedral variety that's better suited for studying independent tensor matrix. And there's also a type B version, which I also have a little model for. You take the type B bio group, generic points, towards the closure. The stellahedron is kind of boxy, and so making these sort of things is not very I don't know. I don't know how to make it very pretty. So like I mentioned, this should be kind of expected if you know the literature. In particular, this is sort of categorification of K-theory calculations. People have found basis for the K-theory. In particular, the work I really like is the work of Dirksen and Fink, which didn't prove it quite in this context, but they're 2 sentences away. And this was later categorified, or rather extended to the Sanchez variety and to the type B Permutahedral variety by people in this room or people who will be in this room at some point. And so these are very nice varieties and explicit calculations. Once you have such things, you get quivers. And so this is the quiver for the Sanchez variety, SL2. These quivers are very easy to construct based off the pictures. And in fact, they actually have a purely matrix-theoretic description. The vertices correspond to the Schubert matrix, and the arrows in this case correspond to something very close to weak maps. I need to tell you how to write down the labels, but that can be done fairly easily. All right, so what's next? Well, there's 2 projects I'm really interested in. The first is trying to do this for other varieties. In particular, I care about a specific variety. I want to do the toric variety of Loday's associahedron. Okay. There's a lot of reasons to care about this related to wonderful varieties and so on, or maybe just intrinsically if you care about the associahedron. I've tried a couple of things, some polytopes coming from cluster algebras and other from the group cosets, and everything has failed. So I kind of want to ask the audience if at some point, if you know any family of deformed associahedra of size L and many polytopes, come talk to me. So by dimension reasons, we know that such a collection must have the number of vertices of the polytope. And so we know that we're looking for L and many deformed associahedra. For the 2-dimensional case, we have these things. And the second project, I'm not really ready to write too much about, but I'm trying to calculate derived categories of wonderful varieties and maximum building case sets. Since these varieties sit nicely inside the Permutahedral variety, you can do push-pull type arguments. I have small calculations, and so far, the derived category does not seem to depend on the actual hyperplane, but only the matroid, which would be very nice, although this is still very, very much in the air. And that's all I have to say. So thank you for listening.
Right. What is the Loday's associated?
Yeah, so Loday's associahedron is a very specific realization of the associahedron, which is important to combinatorialists because it shows up in cluster algebras. It also shows up in opera theory, I think. I can show you a picture.
So in your main theorem, there is an implication. I mean, how does the, I mean, not fullness, but let's say strong exceptionality to your condition relates? I mean, is it far away, or for other toric examples? I mean, there are many examples where there are full strongly exceptional collections. Does your criterion always apply, or is it really just implication that works in many cases?
Yeah, so for strong exceptionality, this is directly calculating the extensions, so it's 1-to-1.
Okay.
For fullness, the thing that happens is that in the coherent constructible side, you have these skyscraper shapes of polytopes. And so if you have things that look like subdivisions, you get certain exact sequences, which is where you need to prove fullness. But there, I only use special classes of exact sequences. I'm sure this is not if and only if fullness. But for strong exceptionality, for sure, it's the same sides.
All questions.
There is this conjecture that relates semi-simplicity of quantum homology for varieties with existence that in collection.
I know nothing about it. Yeah, this is very much the first step. There's lots of very interesting questions that I would love to answer for the Permutahedral variety, such as this. Something I should mention, you should notice that the collection I chose for people who know about matrix theory, that collection is invariant under all the symmetries of the fan. And that's true for all the examples. And there's also conjectures relating that sort of things for toric varieties. Lots of interesting conjectures I don't know how to answer.
Were you taking Schubert matrix with respect to a fixed flag?
That's right. Yeah. So no. So I should mention this. So for me, a Schubert matrix is up to all choices of flags. In terms of the polytopes, these are commuter Schubert matrix, maybe. You need to have n factorial of these. And if you take the normal ones, there's not enough. Okay. There's up to all permutations, which is why it's SN invariant.
Okay, that's fine.
And then it's invariant under the Cremona symmetry because of duality matrix.
I have another question. The quiver that you drew.
Yeah.
Yeah. Is this the quiver with relations, or it's like an honest quiver?
It's a quiver with relations. The paths which the union of the labels agree are the same. So this path here and that path there are the same.
Who made your permutations?
Me. I made it. Um,
How do you make it?
so I printed out the net and then cut out felt from Joanne's or something, and then sewed it, backstitch. It takes me forever, so I'm very sad. I made some for my advisor when I finished my PhD. I made 3 of these for Permutahedral. This is the worst one. I failed to properly color it. I'm slightly colorblind, so I have an excuse. But for the other 2, I properly colored them properly, and that went to Federico and Lauren Williams. They have the good ones.
All right, thanks and thanks for all.